Right. So we've been talking about importance sampling so far. And one of the last topics we'll do in importance sampling is going to be weighted importance sampling. And it's a pretty interesting estimator and a pretty interesting technique, quite magical in the way it works. So here's the situation. So for many distributions, and hopefully we'll get to some of those situations at some point, but in many situations, for many distributions, we often don't know the target distribution fully. Okay, so we're not aware what the target distribution looks like, but we have to know something about it. And what we know about it is that we know it up to a normalizing constant. Okay, so we can figure out a constant up to which um, we know the density. What I mean by that is that our target density, recall we've given notation f of x. We don't know f of x in the sense that we know it is a times f tilde x, where this part, f tilde, is known, okay, but a is not known, okay. So this a is unknown, and this happens often in areas of statistics and machine learning called Bayesian statistics. And often we turn to something called weighted importance sampling in this case where we use the proposal density g of x, which again we can write as some b times g tilde x. Okay, and oops, okay, b times g tilde x, where b in the proposal may be known or unknown. So it may be known, it may not be known. Okay. Now, for simplicity, just because we know that we don't know A, we will also assume we don't know B. Okay, so let's give an example. So, for example, f of x, we can talk about normal 0, 1. Okay, so in this, f of x could be, I know, square root 2 pi e to the power minus x squared by 2. But what we could have is we know f tilde x, which is e to the power minus x squared by 2, and we don't know the constant associated with it. That is, we don't know 1 over square root 2 pi. Okay? Oops. So that's the situation we find ourselves in. Okay? Now, what can we do? And what is the goal? Our goal is, because it's importance sampling, I should remind that the goal is still the same as it has been in the previous videos. There's a function h, and what we want to do is we want to find the expectation of h with respect to f, the distribution that we don't know fully, the density we don't know fully, and we want to use g as our importance distribution. H times f by g times gx is exactly what theta is. This is the trick we used in simple importance sampling. This is the situation we are in again. But the issue is, since we don't know a and b, we can't evaluate f of x and g of x. And so our original importance sampling estimator, which would have been 1 over n, summation t going from 1 to n, h of zt, where I should remind that z1 up to zn is IID from g, f of zt by g of zt. But the issue is that even if we know g completely, we often don't know f, right? We don't know the a in f, so we can't actually evaluate this. Right? What we can evaluate is f tilde and g tilde. We can't evaluate f and g, but we can evaluate f and g tildes. So if we could estimate a and we could estimate b as well, then that would allow us to estimate theta, right? Because if we could estimate a, we could take that a and the f tilde together to get my f. What we'll actually do in weighted importance sampling is, instead of estimating a and b separately, we will estimate b by a, which also is going to work. So specifically, here's the setup that we have. I have z1 up to z, this should be zn, that are IID from g. Okay, and the weighted importance sampling estimator of theta is then defined as This numerator that I'm familiar with, summation t going from 1 to n, h of zt, f tilde zt divided by g tilde zt, right? So this looks like the usual simple importance sampling estimator except with the f tildes and g tildes. Divided by summation t going from 1 to n, f tilde z, g tilde z, right? So there's an extra term in the denominator, and you can think of having 1 over n and 1 over n over here, both, which wouldn't really matter because you can cancel these out. And this is the weighted importance sampling estimator, which is a different estimator from the simple importance sampling estimator, right? So now our first result is that as n tends to infinity, theta hat w tends to theta. Right? Theta hat w is our weighted importance sampling estimator. As n tends to infinity, this becomes closer and closer to theta, which is great, which means that our weighted importance sampling estimator for large samples is expected to converge to our actual quantity we want to estimate. So that's fantastic. How do we show it? It's actually not too complicated. So here's how it works. So as a first setup, okay, we note that as n tends to infinity, by the law of large numbers, I have that 1 over n, summation t going from 1 to n, h of z, f tilde z divided by g tilde z, just by law of large numbers converges to its expectation, right? Which is this quantity here, right? And the denominator 1 over n summation t going from 1 to n, f tilde by g tilde converges to its expectation. And that's just from a law of large numbers. Okay. We also then have, by the application of continuous mapping theorem, we can take this divided by this, which then would converge to this divided by this. Now, this first expression divided by the second expression is nothing but theta hat w. So we get theta hat w converges in probability to this expectation divided by this expectation. And now what we want to show is that this thing is nothing but theta. Because if we can show that, then we know that theta hat w converges to theta. Okay, so what I'll do is I'll calculate the above expectation first, and then I'll calculate the below expectation second. Okay, so let's calculate the above expectation first. So this thing over here is integral h f tilde z g tilde by g times g dz, right? It's integral with respect to g because I'm taking samples from g. But now this f tilde and g tilde are actually not densities, and I would like to cancel these two out. So in order to cancel those two out, I want a b here, which means I'll have a b left over. And then while I'm at it, also divide by a, and I'll have a left over here. Okay. Now this b tilde times b times g tilde is nothing but g. And there's a times f tilde is nothing but f. So I get b by a equals integral of h f by g gz dz. This gets cancelled, and now I just get integral of h of z f of z dz, which I know is nothing but theta. So I get b by a times theta. All right. So my numerator over here has turned out to be b by a times theta, which means what I want this denominator to actually be b by a. Because if this denominator becomes b by a, then b by a gets cancelled, and I just get theta. So let's look at this. Hopefully it'll turn out right. So I have this expression over here. This is this integral. I again multiply and divide by b by a, and I get this. Then finally that g and g will get cancelled, and I'll get b by integral of f z dz. But because this is a density, this whole thing is 1, so I just get b by a. So that's great. So I've gotten b by a, and so this ratio turns out to be b by a by theta divided by b by a, which is exactly theta. So I get the theta hat w converges in probability to theta. Okay. However, it's a little bit sad. So we do have consistency in the sense that as we get more and more samples, our estimator converges to the correct value. However, we don't have unbiasedness. So the weighted importance sampling estimator is in fact a biased estimator. which means that for any finite n, there is the expected value of theta hat w is not going to be theta. So there's going to be some difference in where the estimator is located. However, what's pretty nice is that often, this is not always true, but often the weighted importance sampling estimator can have smaller variance than the simple importance sampling estimator. It's not always true, but often it can have a smaller variance. Okay, so let's take a look at an example. This is a two-variate example, so it's a bidimensional example. So consider estimating the integral 0 to pi of xy f of x comma y dx dy. Okay, so this is my integral. Looks fairly complicated, where particularly f of x comma y is e to the power sine xy. Okay, where x and y are both between 0 and pi. Now, I say f of x comma y is proportional to this. Okay, because I don't know what the proportionality constant is, and you can figure out that if you want to do integral 0 to pi of e to the power sine xy dx dy, you'll see that it's not that easy to find out, which means one doesn't quite know what this value is. Okay. Further, the target distribution is also not a product of two marginal distributions, so it's not decomposable. So x and y are not independent of each other, because you can't really decompose this as some function of x times some function of y, right? So we have to implement something a little bit more complicated, but the principles are exactly the same. Okay. So there exists some a such that f of xy is actually a times e to the power sine xy, and we don't know this a, that's okay. Okay. And given that this is the actual value that I want to estimate, and x comma y is next to my proper density, I have my h function, h of xy is equal to x times y. Right? And again, because we don't know this, we can't implement simple importance sampling. So instead, we'll implement weighted importance sampling. Okay. Now consider a proposal distribution or an importance distribution to be the uniform distribution on 0, pi and 0, pi. Now the proposal distribution needs to be defined in the same support as my target distribution, right? Which means x and y is between 0 and pi. And so let's say I propose that, right? I propose the uniform distribution between 0 pi, so that g of z comma t is 1 by pi square, indicator z between 0 and pi and t between 0 and pi. Okay. Now here, this 1 by pi squared in g is known, but we'll assume that we don't know it, right? Which means that I can write g of z comma t as some b times these indicators. Okay. And this b, we will assume that we don't know. Okay. So now we're ready. We have everything set up. We have our f of x. We have our unknown a. We have g, our proposal density. We have our unknown b. And we also have the h of x function. So now what we need to do is propose values uniformly from this, which we've already learned how to do. So we get the tuples z1 t1 up to zn tn from uniform 0 pi cross uniform 0 pi. Okay. Then the weights, remember, are f tilde by g tilde is what I define the weights to be. So the weights wzt comma t sub t is f tilde by g tilde, which in this case g tilde is just 1. So this is not needed. I just get e to the power sine zt t sub t. Okay. So I have these weights, and now I'll just put it in the simple importance sampling estimator. The final estimator is h, which is ztt, weight w, which is f tilde by g tilde, f tilde by g tilde. That's it. This is my weighted importance sampling estimator. Fairly simple. Okay, and I can actually implement this as well. I set the seed. I always set C to ensure that what the simulation result that I get is exactly what you're going to get as well. N, the number of times I'm going to simulate, number of samples I'm going to simulate is 100,000. 1 lakh, I'm keeping it large just so things are a bit stable when I implement things. And the WIS, the weighted importance sampling function, is defined as the following. First, I get my samples, which are going to be Z and T. So this is what I'm trying to do here is I'm trying to do ZT, T sub T is what I'm trying to sample from, T going from 1 to N. So notice the number of samples that I get is actually 2N, right? These are from uniform 0 to pi, both of them, and they're independent of each other. So I'm just generating 2 times n of them. The first n I will give to z, and the second n I will give to t. Right. So the first n, the head of the sample, the first capital N, I give to x, which is essentially my z, and then the last n I give to the second component, which is essentially my y. And what I'm going to return is actually the weights W tilde, the W F tilde by G tilde. So this is F of ZT by T sub T, which is F tilde by G tilde of the corresponding, right? Which is just e to the power sine xy, which is what we've gotten. And what I return are the weights and also the samples themselves. So x comma y, the tuple. So this thing over here is just going to be a matrix, okay, where there's going to be z's on this, t's on this, and there's going to be n different rows. Okay, and then I call this function. So I call this function and store the output in output. So output now contains my weights, my W tildes, and all my samples, which means I can go and obtain theta hat W from my samples and from my weights. How do I do that? Well, my estimate is just going to be mean, right, so the numerator divided by the denominator. The numerator is the first element of the samples, which is z's, times the second element, which is t's, times the actual weights, right? So this is zt, t sub t times the wt, divided by, so the mean of this whole thing, divided by the mean of just the weights. And when I take an average of that, that turns out to be 2.148, right? So my estimate of this particular integral of e to the power x comma, what was it? E to the power xy, f of x comma y is equal to 2.15 essentially. Okay, and what's really interesting is I didn't actually know f completely, but still I was able to estimate this integral, and that's pretty cool, right? We didn't know it, but we were still pretty much able to estimate it, right? Okay, and that's one of the reasons why the weighted importance sampling estimator is so powerful, is despite not knowing the full target density completely, we can still estimate various things about it using the fact that there's this new portion in the denominator in the estimator. Okay, here's some things to think about. How would you choose a good proposal for weighted importance sampling? The issue is that the variance of weighted importance sampling estimators are no longer the same as the variance of the simple importance sampling estimators. So the proposal that was optimal in the simple importance sampling setting may not be now optimal anymore here, and it's unclear as to what would be a good proposal in this particular weighted importance sampling setting. Okay. Second is, do you think you can implement the above example and convince yourself that weighted importance sampling estimator is biased? So remember I said the weighted importance sampling estimator is biased. And we verified the unbiasedness of the simple importance sampling estimator in a previous video. Now, using that same methodology, do you think you can construct an idea to actually verify visually or through some other means that this is in fact a biased estimator? So see if you can try that. Okay. And this really brings us to the end of important sampling as well. So now we've pretty much finished sampling from some distributions, and we've also done some aspects of what do you do when you sample from those distributions using important sampling. The next phase, which is what we'll start in the next few videos, we are going to pivot to the ideas of optimization, and we're going to do a lot of optimization for the next few weeks. So that's going to be the next set of videos. We'll start talking about it starting next week's next video itself.